significant heterogeneity in the algorithms used. People were using inconsistent algorithms. They were using inconsistent validation methods, and the results were very different between them. To give an example of that, we go back to the definition by Catrona et al. And as I said before, this is their definition for a phenotype algorithm. For myocardial infarction, codes of 410.xo or 410.x1 in the primary position. Their method for evaluating that was to have cardiologists review the user information abstracted from the hospital records to assess the likelihood of the AMI. So they had cardiologists review the chart reviews. And then finally, they came up with that. They came up with a PPV, a positive predictive value of 86%. In another study by Choma et al., they used a different definition where they also used 410.x instead of 410.x0 or x1. And they also required a hospitalization stay of greater than 2 days. Their method for evaluating was based upon a history of chest pain, EKG, cardiac enzymes, and once again, they found the positive predictive value. In their case, in their study for their single database, they found a positive predictive value of about 93%. Finally, we showed the example from Ryu et al. And they were a little fuzzier on their definition for their phenotype algorithm. They didn't quite precisely give it in the paper, but they did look at the way they evaluated the ones that their algorithm selected. And that was a criteria of chest pain, ECG findings, cardiac enzymes, and cardiac angiography or nuclear scan. And in their paper, they found a positive predictive value of 76%. This is some of the overall results that you see from the Robo paper. And you see a wide range of values for positive predictive value through all the different papers, ranging from about 20% to about 100%. And we see the three examples that I had given before, somewhere in the middle within those ranges. One of the issues with traditional validation is it's time-consuming and very costly. And to give an example from Catrona to show how much work this involves, they had to request patient data from 4 different data partners. Then they had to have 2 trained nurse abstractors review all the records from the data and come up with standardized abstraction, which included things like sex, age, race, and a lot of the clinical markers like EKG images and cardiac biomarkers. And then they went through an adjudication process or a reliability process where they reviewed the first 10 cases between the two to look at inter-rater reliability. Then, it's still not done yet, then they had to create the adjudication protocol based upon the American College of Cardiology task force. And then 2 cardiologists reviewed the abstracted data that they had to perform, that they had previously abstracted. And from there, they were able to define whether people were definite MI, probable MI, did not have MI, or were unable to determine. A lot of issues with this process. One, they had to request patient data from 4 different data partners, and that's time-consuming to receive the data. There's also the possibility of selection bias because not all the data will be received back from the data partners. There's also issues with classifying the cases. They had a definite, a probable, but there was also unable to determine. And in the case of Catrona, 10% of their subjects, they were unable to determine whether the subjects had MI or not. At the end of this process, they had 143 patients that they reviewed and classified as either probably, definitely, or did not have an MI. The conclusion of this is that Robo found was that for MI, there's really no gold standard algorithm available. The process is costly and time consuming, And you have small sample sizes, which means that you're going to have wide variation in the estimates and wide confidence intervals. The other thing they found in the 33 studies of validating the algorithms, all reported the positive predictive value, but only 11 reported sensitivity and 5 reported specificity. And the question is this really validation? So in traditional validation, you get the positive predictive value and you rarely get sensitivity and specificity. And the reason why that is that positive predictive value is the easiest to assess, and that sensitivity and specificity are much less frequently reported. The reason why that is that it's a high cost and time to evaluate for sensitivity and specificity. Whereas positive predictive value, you can just pick out, 100 or 200 cases that you're looking at, that your algorithm picked out, and just have them look at the cases. For sensitivity and specificity, it becomes much more complex. So to give an example of the complexity, so for determining sensitivity through chart validation, let's say the prevalence of MI in a population is 1%. And you expect a sensitivity of about 75%, meaning that 25% of your cases are going to, 25% of the cases are not going to be included in your phenotype algorithm. You will have missed those. Those are your false negatives. With that, you need to review 10,000 subjects who were not included in the phenotype algorithm to find 25 false negatives, to be able, and from there you could then determine your sensitivity. So that's a huge task, and you're not going to get 2 clinicians and all the nurse abstractors to be able to do 10,000 subjects. The problem is that sensitivity and specificity are the actual characteristics of the test, whereas positive predictive value is a function of sensitivity, specificity, and most importantly, the prevalence of the health outcome of interest. And I'll give you a couple examples on why it's important. So let's say you have one test, and we know the sensitivity and specificity, sensitivity of 75%, specificity of 99.9%, almost perfect. And you have 2 different populations of 10,000 people. The first population has a prevalence of 1%. And with that sensitivity and specificity, the positive predictive value would be 88%. The second population, where the prevalence is 5%, that using that same test, the positive predictive value would be 97%. As another example, where you have one population but 2 different tests, and all you know is the positive predictive value, you could have a positive predictive value in one case where the sensitivity is 18%, and another case where the sensitivity is 72%. So just giving you the positive predictive value does not cannot clearly define the sensitivity and specificity for you. So once again, the problem with traditional validation that you need 4 different pieces of information to validate an algorithm: sensitivity, specificity, positive and negative predictive value. But for traditional validation, you basically only get positive predicted value. The question is, we have to live with these algorithms. Algorithms are used in most research and observational data, so we can't do away with them. And there's many ways to define an algorithm for any health outcome. As anybody who's tried to develop phenotype algorithms, there's dozens of ways that you can do it. Each definition will have its own performance characteristics: sensitivity, specificity, positive, negative predictive value. You need to validate that algorithm to be able to understand these characteristics. So validation, and once again, so validation through chart review and observational data is costly and time consuming, and the biggest problem is that the data is not usually available. For a lot of our data sets, we can't get at the chart review. And traditional validation provides incomplete results, mostly positive predictive value, and that's prevalence dependent, as we showed before. So the question is there an alternative to a traditional validation? And one of the things that we thought about is whether that alternative could be diagnostic predictive models. And diagnostic predictive models are used to estimate the probability of having a particular disease or outcome. So we developed a tool called PheValuator, This is the first paper that we published a few years back, where we did used the first version of PheValuator, PheValuator 1.0, and we laid out the framework for how the process would be undertaken within the package. Just recently, we published our second paper. This paper showed methodological improvements to PheValuator. We did PheValuator 2.0 on this. And one of the things that we did in this paper is that we assembled a set of previously traditionally validated studies for about 18 different phenotypes. And we compared the results from the traditional validation to our results from PheValuator. And what we found was that for positive predictive value and specificity, the results from PheValuator, the new version 2.0, came very close to the results from the traditional validation. And our conclusion was that PheValuator 2.0 can now estimate positive predictive value and specificity within 5% of traditional chart review, but without requiring review of the charts and all the cost and time associated with that. I'm going to go into a little bit about how the tool works. So a predictive model is developed using a set of labeled data, and the labels represent whether the person has the case or does not have the case for the health outcome. The thing with the models is that the more accurately you make those labels, case or non-case, the more precise the model will be able to determine the predictors that will allow you to discriminate between those with the health outcome of interest and those without the health outcome of interest, the cases and the non-cases. So in our method, we wanted to assure that when we built the model, we only include cases that were very likely to where we knew the label fairly confidently, a high probability of either being the case or not being a case. So here's the way we did that. So imagine the large rectangle is all the subjects in a database. The yellow ones are people who are not likely to be a case. The orange ones are people who are probably a case. And this green set here, the sweet spot, are the people who are very likely to be the case. So we wanted to find the green ones who are very likely to be a case and the yellow ones who are very likely not to be a case. And we did that by developing several phenotype algorithms to separate the populations. To figure out the orange ones who were possibly a case, we used a sensitive algorithm. To figure out the green ones, we used a very specific algorithm. And the yellow ones were the people who weren't in the sensitive algorithm, weren't in the orange or green boxes. So in the end, we ended up something like this, where we have this cleaner comparison between the yellows and the greens. And now we feel that with this separation, now we can correctly label the subjects who are in the model to be cases or non-cases, and we can get better performance characteristics. So, for example, the way that we constructed the algorithm for the very sensitive phenotype algorithm, we looked at subjects who had at least one occurrence of the condition code. So for myocardial infarction, we looked for people who had one condition code of myocardial infarction. For the very specific one, we upped the ante and we looked at 2 occurrences, the condition code, in a very short period. And we felt that this was a way to make a more precise algorithm, more specific for the condition. Using the Atlas tool within the Odyssey tool stack, this is an example of the way we created the phenotype algorithms for myocardial infarction, where we looked at 2 codes of myocardial infarction within a short period of time. Then within the modeling process, we used the model then can pull out predictors for the health outcome. And the way we built that is that, imagine this is the timeline for the person's in the person's history. We have 3 predictor windows, each of 10 days, and we pull out features within each of these 3 windows. And that allows for a good precision of the model using those characteristics. So some of the potential data elements in the models that you might find in these windows, you might find the health outcome code, for instance, myocardial infarction, or other conditions that increase the risk of disease. You might find signs and symptoms, diagnostic testing, acute treatment, chronic treatment, follow-up care, and sequelae for the disease. And here's how in the first step, we're creating the diagnostic predictive model. Remember, one of the goals was to make it clean between the people who are cases and the people who are non-cases. So imagine these 7 subjects here. We have 3 subjects who have question marks, who are in the extremely sensitive cohort. We call it the X-sense cohort. 3 subjects, and 2 of those subjects were also in the X-spec cohort. And the rest of the subjects were in either the X-spec or the N-sense. This is the number 7 here is the questionable one. We don't know whether he's a case or not a case. So what we do is we eliminate that person from the model. And then we can more accurately label these 6 people who are left as being cases 1 or non-cases 0. We then can produce the diagnostic predictive model from there. And this is sort of a stylized version of what you get from the diagnostic predictive model, where you might end up with 3 predictors and with all different weights. These are essentially the beta coefficients from the logistic regression model. Some of the things that you may find as potential elements in the myocardial infarction, you might find health outcome codes. So for instance, having a diagnosis code of myocardial infarction itself is a good indicator, a good predictor that you actually have myocardial infarction. But that's not the only thing. You might want to look at other instances of other conditions like hypertension, diabetes, which might also be strong predictors of having the myocardial infarction during that time. You look for signs and symptoms like chest pain or dyspnea, diagnostic testing, acute treatment like CABG, or stent, chronic treatment like antiplatelets and cardiac rehabilitation, and then some follow-up care, and then some sequelae. So these are some of the potential elements that can come out of the model. And what we see is that some of these are going to be specific for MI, and some of these are going to be non-specific. And the more with these models, the more specific they are for the condition, the better the model is going to be able to predict. So in this case for MI, we actually have a lot of these green check marks, which indicate that are very specific for myocardial infarction. Here's an example of the model that came out from a LASSO regression for MI. And some of the things that you see in here are, so myocardial infarction is one of the best predictors, and this is the beta coefficient from the model. Pharmacy visits are a good predictor, chest pain, prior heart disease. And then if you go down, you look at things like anti-clotting mechanism, drugs, prasugrel, other tests that might have been done, and then some long-term follow-up things like other antiplatelets, and maybe statins for lipids. So this is the model that would have come out. The next step in the process is to develop the evaluation cohort. So now we have the model, and the model can give us a method to figure out if a person has myocardial infarction or not, or the disease or not. The next thing what we want to do is we want to create a large group of people to be able to start the assessment for our phenotype algorithms, because that's the ultimate goal, to be able to test the phenotype algorithms. So let's say this is all the people in your database. We select a large subset of that. In some cases, we select 2 million people to be able to work in there. Then going back from before, we have our predictors and weighted by their beta coefficients. And then we take the new set of people that we randomly selected from the population for our evaluation cohort, and we look at their records. And we find that we then apply the model to their records. And each one of them will have some level of, either they'll have predictors or not have predictors. And from there, we can then figure out the probability based upon the model. We can figure out the predicted probability of them having the health outcome of interest. So for instance, in subject number 11 here, they had all three predictors, and that gave a hypothetical probability of 100% of them having the outcome. Number 12 had no predictors, so that was a 0%. And other ones are somewhere within the range there. So now we have, so now we can now start testing the phenotype algorithms. We have the model. We have a large group of people who we have the who we have a predicted probability for them having the outcome for each one of them. And now we can start using that data to start testing the phenotype algorithms. So here's our full data set again, and here's the subset that we pulled out. And the people in red are the people that the algorithm selected within that subset. And now we can look at the people who the algorithm selected and the people the algorithm didn't select. And that can give us the performance, start to give us the performance characteristics of the phenotype algorithm. So there's the set, there are the people. And then we look at the people that the algorithm selected and the people that the algorithm didn't select. In this case, the red crosses are the people that were included in the phenotype algorithm. The black X's were the people who were not included in the phenotype algorithm. And so now we know the predicted probability of the people that were selected by the phenotype algorithm and were not selected by the phenotype algorithm. We can then use that data to start figuring out the true positives, the false positives, the true negatives, and false negatives. The way we do that, we start off with the people that the phenotype algorithm selected, these three people. So take the first person there. The first person had a predicted probability of having the health outcome of 100, or 1, essentially. Perfect. So the probability of that person being a case is basically 100%. And the probability of that person not being a case is 100 minus 100 is 0%. And we do that for each of the other the subjects that the algorithm selected. So in the second one, it was 50. He had a probability of 50. So the phenotype algorithm got that person half right and half wrong. So he had a 50% chance of being a case and 50% chance of not being a case. And what we do is then bucket these results here so that the probability of them being the case, 150 and 0, gets put into the true positive bucket, because this is the algorithm got these correct as saying this person is a positive, and the other side is the mistakes that they made. So so we called this person here a case, where there's only a 50% chance of being a case. So they got 50% in the true positives and 50% in the false positives. For the third one, they got it completely wrong, and they put 100% in the false positives. You do the same thing for the people that were not included in the phenotype algorithm. So you go through each one of these. So if somebody has a probability of being a case of 0%, they have a probability of being not a case of 100%. 100 minus 0 is 100. So then you do the same thing here. So the chance, so somebody who has a 30% probability of being a case has a 70% probability of being not a case. 50% probability of being a case, 50% probability of not being a case. You use these numbers here to bucket and become the true negatives and the false negatives. So in this case here, so the person who was a 0% chance of being a case, a 0% chance of being a case, or 100% chance of being not a case, since the phenotype algorithm did not select this person, you put 100 in the true negative bucket. And you do that for all the subjects that are in there. You can then take those numbers that you got from your true negatives and false positives and all, and you can create your confusion matrix, where we look at the truth at the top and the test at the bottom. So now we have our true positives, true negatives, and false negatives. And from there, now that you've completed the confusion matrix, you can then calculate your sensitivity, specificity, positive and negative predictive value. So as a review of the process, so we start off with a clinical definition to evaluate. We create our X-spec and X-sense cohorts to be able to say who's probably a case and who is probably not a case. We train a predictive model using those cases and non-cases. We take a large random sample of people. We apply the prediction model to that large sample to get what we call a probabilistic gold standard. So we have a large set of people, each with a predicted probability of having the case, of being a case. At that point, then we can go back and evaluate the cohort definition, the phenotype algorithm that we wanted to evaluate. And we can evaluate, once that evaluation, we can develop positive predictive value, sensitivity, specificity, and negative predictive value. These are the results that we showed in our most recent paper for PheValuator 2.0. Just to give you an orientation on the y-axis, you have the set of health outcomes that we looked at. On the x-axis, excuse me, you have the positive predictive value. The x's were the benchmark. Benchmark were the clinical validation studies that we use to compare PheValuator to. And the red dots are PheValuator. And we see good overlap between the blue X's and the red X's, meaning that it was relatively good concordance between what we see in PheValuator and what we see in the phenotype benchmark. We did see some exceptions, though. So, for instance, atopic dermatitis, we seem to have higher prediction than what was done in the clinical studies. So one of the things that you notice is that with myocardial infarction, we had a lot of green checks in here to have things that were fairly definitive for myocardial infarction. But if you look at a condition like atopic dermatitis, we don't have that sort of thing. If you look at, the health outcome code for atopic dermatitis, that's very specific for atopic dermatitis. But other disease that can cause risk, asthma is not very specific. There's no real good diagnostic testing for atopic dermatitis. The acute treatment, for instance, corticosteroids, is very nonspecific. It can be used for a lot of dermatological conditions. And you go down the list and we see a bunch of fairly nonspecific things for atopic dermatitis. And this is one of the things that we find. If the data in the database is not very specific for the health outcome of interest, the predictive model is not going to be able to determine its accuracy very well. There are limitations to PheValuator. One of the things that we found is with sparse data. If you have sparse data in the system, the model is not going to have much to work with, and you're not going to be able to get accurate models. This is also true with traditional validation. For instance, in Catrona, 10% of their patients had insufficient evidence, and Ryu, 7.5% of their patients had insufficient evidence. The other thing we find is that databases vary with overall level of detail. So some databases have a lot of information that are good. You might see more drugs in certain databases than others, that type of thing. One of the things that we found, and there's a subtle difference between what PheValuator is doing and possibly what the clinical validation was doing. What PheValuator is doing is estimating the probability based upon whether the subject's clinical team that they were working with and what was put into the data set whether the clinical team thinks that the person has the diagnosis and is subsequently treating them for it, along with things like signs and symptoms. What it's not giving you is whether the person actually had the heart attack or didn't have the heart attack, the absolute truth. What we're giving is the best estimate based upon the way the clinical team looked at it. And if you see in some clinical validation studies, they're actually going back and assessing how well the clinicians diagnose the person. And this is not what we're doing. So for certain health outcomes, they may change the diagnosis and say that the clinical team was wrong. What we're assuming is that the clinical team is right based upon the fact that they diagnosed them with it, that they've treated them for it, and that they had a significant number of signs and symptoms indicative of the health outcome. So in conclusion then, using diagnostic predictive models to assess algorithm performance produces estimates with good agreement with previously published validation studies. That's what we saw in our most recent paper. The important thing about this is that having these metrics for phenotype performance increases the confidence in the use of our data in research. That the phenotype algorithms, we have a sort of a gold standard that we can meet against for each of the phenotype algorithms to see how well they perform. This then leads to the potential to be able to use the results from the phenotype algorithm, the performance characteristics, to be able to ultimately correct and adjust the estimates. A lot of this, this comes down to correcting for measurement error and misclassification, whether the code is the phenotype algorithm gets the code right or not. The misclassification leads to measurement error, and that measurement error could come out in things like incidence rates and effect estimates. And ultimately, having all the data from PheValuator, sensitivity, specificity in particular, we can then correct incidence rates and effect estimates. PheValuator is an open source tool in the Odyssey tool stack, and you can download it from the Odyssey GitHub repository. It gives you examples in there on how to use the tool, as well as all the full code that for using it. And with that, I'll conclude and say thank you and ask for any questions.
Thank you, Joel. Does anybody have questions? I see David, your hand is raised.
Yeah, thank you, Autumn. And first of all, thank you, Joel. I very much congratulate you for this tool. I think it's one of the most wonderful R packages in Odyssey currently. I have one question with regards to the when you compare the results of PheValuator and the results of the clinical validation studies. That it seemed to me that the PheValuator results are less variable compared to the clinical studies. The variability of clinical validations is much larger than the variability of evaluation.
Right.
And I wonder whether that's an artifact of using large samples in PheValuator for predicting and for the comparison, or it's I mean, matter of the actual accuracy of PheValuator. And also, what implications, in your opinion, does that have in terms of generalizability of PheValuator?
Yeah, it's a great question. Thanks, David. So some of the things that we see is that the testing that we did on the clinical tool, the people who did those clinical studies were done on a specific database, and that's not the database that we have. So there is going to be some variability between the databases. Our databases tend to be a bit more consistent than these. There's also a wide range of things that we saw. Most of the database that we saw were that we used were from the United States, whereas some of the studies were from outside of the United States. So there's some differences there. But overall, the consistency is, we did see, especially with if you look at the Rubbo paper, across that, we see a wide range of variability in the different studies that they saw for myocardial infarction, and we do see better consistency within PheValuator. Thanks.
So a comment in the
I had a
chat.
question. Oh, sorry.
Go ahead, Jennifer.
No, I had a question. Maybe I missed this. Well, two questions. First question: do you have to use PheValuator? Do you have to have an external validation that's already been conducted? Number one, and number two, do you have to use the package on data that's been transformed to the CDM, or can you use it on other data sources?
Yeah, so it's a great question. The at this point, we don't feel that we have to have external validation for a lot of outcomes that we're looking for. There are no external validation studies out there. Basically what we did with PheValuator 2 and the PheValuator 2 paper was to do this comparison between external validation. We are looking to do some further validation of PheValuator, possibly doing some chart reviews on some small samples of subjects. So second question, yes, all the tools in the LSC tool stack rely on the OMOP common data model to be able to be performed. Yeah, so that is a requirement.
Joel, this is Kevin. Just a couple questions. One on, that's very much predicated on having complete data, especially. So our claims data is great, closed claims with regards to very defined enrollment periods for medically attended events that people aren't going to pay cash for. So you're going to capture the event in its totality. How do you promulgate that users should probably not be using these methods if you have EHR data only? And my question there was like, if I get all my AMIs at an Epic EMR and all my rheumatoid arthritis exposures at a Cerner EMR, this is not the tool for you, because if you get your AMI and you don't know it, then you don't have complete data to do the predictions.
Yeah, no, I agree with you, Kevin. We definitely do see differences for claims data versus EHR, especially on emergent conditions like AMI. As somebody's having an AMI or a stroke, they're getting taken to the nearest hospital, and it may not be in the EHR system. So you're going to be missing data from those people. We do see more consistent data, more consistent results between EHR and claims for non-emergent care for chronic conditions. So there is that in its favor. But you're right, the EHR, if they're not in if the provider's not in the EHR system, that data is going to be missing.
And then just another follow-up question on if, especially with urgent events, right, where I may go an entire year without an office visit. I may have gotten vaccinated, but that doesn't rise to the level of an office visit if I got it at an outpatient pharmacy or something. And so but yet I am at risk, right? And so if I have the event, I get to play with your data, right? But if I don't have the event, is my predicted probability for that given year, 0? I'm thinking of things like appendicitis and those types of things, and also raising that level of, especially with our claims data that have probabilistically sort of short time windows, right? 1 year, 2 years, maybe 3 years of follow-up time. There's going to be some phenotypes where if you really want the first event, or you want to know, look, my appendix is out, I am no longer at risk for an appendix, stop predicting that I might have appendicitis. It's impossible for me to have that, but your data doesn't know that because it doesn't have that, birth to death pieces. So I think there's going to be still some outcomes that are going to really sort of hang up in some of this work.
Yeah, so appendicitis then becomes an emergent condition, and so the phenotype algorithm, if you had your appendicitis done 10 years ago and you have no issue, no appendicitis records in your data set, the phenotype algorithm is probably not going to, it's definitely not going to pick you as a case. On the other hand, since it's not picking you as a case, when I pick a random visit from you during your time period that you're in there, there's probably very little evidence that you had an appendicitis during that case. So the chance of you coming up as a case and interfering or coming up as a false negative within there is also low.
Right, but what implications does when you mandate that someone has a visit? By definition, people who have visits have probably a higher Charlson comorbidity score. Just guessing, right? If you don't have any visits, you're likely healthy and you're a different population. So just what implications does that forced visit have on the predictive modeling? I don't know if you could relax it and say, all right, I'll pick a pharmacy visit. Now, obviously, most people who have a pharmacy visit in a year also have a regular office visit to get a prescription. But for really healthy people that have no office visits that you see, they're comparatively out. Their predicted probability is always going to be 0 for every event, right?
Yeah, and that's true about, if nobody comes in, if you have a person that never goes to the doctor but has hypertension, diabetes, and high lipids, if they never go to the doctor, never gets registered, the phenotype algorithm is not going to pick up this person in the first place. That is one of the limitations of observational data. You are missing the people that, it's the unknown unknowns that you're seeing here.
I see some hand raised. Evan, you're next on the list.
Hey, thanks, Joel. Thanks for all your work on this. It's been really interesting package to get exposed to and to use and to benefit from. I see Juan's also got his hands up. So I had a couple of questions, but I don't know if I'm gonna intuit that what Juan's gonna ask. So I might go to my second question, and that was kind of relates to the definition of expect. It seems like a lot hinges on your expect definition here, and there's a tension in how you build it. There's a certain amount where you from seeing others go through this process where you actually want to leave some features that you think might be predictive out of expect so that they can kind of wind up as candidates in your trained model. I guess the other kind of major tension there is how expect performs actually can do a lot in terms of what you wind up kind of statistically modeling in that population. Like if you wind up getting a reasonable collection of the wrong type of people, it tends to kind of take our entire current process, and then we're kind of working against this trained predictive model. Say, well, if I adjust this, I have a higher sensitivity or no specificity, but we actually might not actually have the right clinical idea modeled in our statistical model. And so I'm just wondering if you guys have run into this, if you've kind of thought about whether there's kind of any requirement to do any kind of profile adjudication or anything to just take a look, even if it's 20 people. If it's expect, you should be case, then there shouldn't it should be fairly quick. But if you're getting some population of the wrong type of person, your entire process from there on in, actually you could invest a lot of time working against something that is not actually what you're looking to model in the real world.
Yeah. I think that's a great idea to be able to look at some of those stuff just to confirm it. One of the things that you do is that the models that were developed in the patient level prediction package are actually pretty, I don't know, I guess forgiving. Is that you don't need necessarily everybody to be perfectly, that they perfectly had the disease. And you don't need everybody not to, all the non-cases to perfectly not have the disease. It allows you to have some wiggle room within there, and it does fairly well within the LASSO regression to be able to differentiate those, even with some amount of error within the labeling of the cases and non-cases. But I do like that idea to go through the expect and just see how well we're doing with that.
Yeah, and I get your tension there. I mean, the noisy labeling thing is something I definitely grok. Like, and if you see some things like, oh, that is, that's a bit of a miss, but it's a very similar type of patient, that'd be one thing. If you're getting something very different because of just something unanticipated in your data, and that happens, then that, those are the things I think would be red flags, and you'd probably want to catch those soon, or earlier in the process, as opposed to kind of waiting until you've done the whole phenotype creation and evaluation process.
Right. The beauty of that is that in the PLP package, in the patient level prediction package, you get the model out, just like I showed on the screen. So if something's wonky in the expect, and we have seen that before, you're going to get wonky things in the model, and you can see, well, wait a second, whoa, and then you can adjust your expect and xsense from there. accordingly. And we have had to do that for certain examples where we see things that for acute pancreatitis, for instance, when we were working on that, we saw things in the model where people were having the model was also bringing up chronic pancreatitis. And one of the things that we had to do was we realized, with that, we need to change the expect, make it a little more sophisticated to also exclude people with non-acute pancreatitis, chronic pancreatitis, and other forms of pancreatitis, and exclude those from the model. And that improved the model significantly. So that's some of the adjustments you can make. But being able to view the model, have a model that you can view, see the results, and then say, there may have been errors in the expect.
And that's a really interesting opportunity to kind of synthesize this work with some of the work that Juan did and that others did in kind of the ideas that went into Aphrodite, with having that expert in the loop that kind of bootstraps the model with kind of two requirements on anchors. And it's kind of an interesting, Sontag wrote a paper about this that I thought was quite interesting. One being that they're highly specific and the other one being that they're conditionally independent. There's actually, it's got there's some neat potential properties and potential ways we could kind of synthesize how we create expect with that notion of learning through anchors, which might be another discussion, but because I know there's others that have questions. But anyway, I think that's an interesting opportunity to kind of iterate this further.
Yeah, I agree.
Aza, you're next.
Thank you. Thank you, Joel. I'm going to go back and ask a specific question about the situations that you mentioned where you don't expect the predictive model to perform well to start with, either because of sparse data or because of the disease itself or the conditions itself is hard to diagnose, just like ectopic dermatitis and I think pulmonary hypertension and stuff like that. Is there is we relying on our expert opinion to say, well, in this is cases where the model is not going to perform well, so we're not going to take these results? Is there something more systematic that we can come out of the model itself that tells us, look, these coefficients are all over the place, or look, that fitness is overfit, or whatever, all these metrics that come from the predictive modeling world that we could use to systematically say, the data is not, the model is not good, we're not going to use it for validation.
Yeah, and I think that's one of the things that we can do and within the Odyssey community and some of the processes that you and Gotham are working on along with everybody else are the actual phenotype algorithm development process. So to use something like cohort diagnostics to give ancillary measures for this data, to be able to say, okay, so this model doesn't look very good. The PheValuator results look strange. Let's go to cohort diagnostics and see qualitatively, does that make sense with what we're seeing? So that's the other thing that you can do to sort of combine these tools to give a better assessment of what's true and what's not.
Joel, I follow up to what Aza said in your response about cohort diagnostic. Is it possible to, in a innovative way, combine the phenotype development evaluation process iteration? So I think a comment that you made to me is it is possible to output persons with their predicted probability. So if we use and say this set of people are less likely to have the phenotype of interest, and this set of people, as predicted, have a high likelihood of having the phenotype of interest. You convert that into a cohort and run cohort diagnostics on it, and you review those. Would that be useful in the phenotype development evaluation process?
I think so. Yeah, you'll see from the results whether with being able to look at them precisely, which ones seem to be the cases and which ones not, and then it's giving an alternate variation of the whole process. I like that idea.
In fact, it goes back to Evan's comment. So if you have an expect cohort and you run a cohort diagnostics on it, and then you have an output that is PheValuator generated that is highly specific, you compare the expect cohort to the PheValuator highly specific based on a threshold value, that might be informative.
Yeah, And typically what I do is I run, when I run PheValuator, you can run you can test as many phenotype algorithms as you want for the health outcome. I typically run the phenotype, the X-spec, to see how well that X-spec perform. And the X-spec should have a, it should have a very high positive predictive value. Low sensitivity, of course, but high positive predictive value. If it doesn't have a high positive predictive value, then it's not, there's probably issues there.
Evan, this is your last question. We have 1 more minute. We'll be done.
Well, I saw Juan's hand went down. I will yield the floor to Juan. Juan, did you have a question?
Oh no, you basically got exactly the same thing I was going to ask. So
okay, fair enough. I'll go back even more basic, and because now we're talking about the different ways we could use X-spec to enhance the phenotype development process. Maybe this has been shown and I just don't know it, but we also kind of are setting a course where we're saying we're going to take some simple labeling function as our cohort definition, and we're going to use a machine learned model to validate it. And then you look at this machine learned model and be, boy, that looks nice. That looks like it performs well. That's my gold standard. You kind of want to use it. And I haven't wrapped my head around, like, have we proved that introduces all kinds of bias in running a prediction study or an effect estimation study to the point where that is just a non-starter? Because I mean, maybe you thought about this because you had to work through building this idea out as part of your PhD, but I haven't completely accepted it. And so it feels like we're using, creating this fantastic model as our validation process instead of using it as our actual cohort definition. I just didn't know if you had any comments there, or maybe you knew about some studies that I didn't know about, like what kind of biases it materially and empirically is shown to introduce.
I definitely don't disagree with you, Evan. Juan and I have talked about this, and I personally, I think, the heuristic algorithms that we develop are, like I said, approximations, and we're testing it against them. We're getting estimates for how well they perform. But would a probabilistic cohort definition like Juan produces with Aphrodite actually do better? Should that be the future of where we go with phenotype algorithms? It's instead of saying and with phenotype algorithms, I know we're short of time, but phenotype algorithms, you can put all kinds of things in there, and all kinds of elements that may help, may not help, but they're still approximations of what you're getting. Here we say whether atorvastatin has this much of a weight that should be given to it if somebody has atorvastatin during this time. So versus putting in statins as as one of the possible things that people can be taking for post MI as in your definition. So I don't disagree with you. I sort of think that's going to be a big part of the future.
Yeah. All right, everybody. It's past 10 o'clock. That's when the meeting closes. So thank you everybody for engaging with this conversation. Joel, thank you so much for sharing your insights, and everybody, this meeting has been recorded. The slides, I'll request Joel for the slides and paste it on the Odyssey Phenotype work group.